ready to add it.
Let's stick with it. Just roll two sticks together.
Oh my god.
It's always like
That's exactly what it is.
sounds pretty easy to me.
Okay, game. Good morning, everybody. Happy Friday for you guys, huh? Thursday for me. Well, okay, let me go through the attendance thing real quick. Okay, oh, that's right, Cody Joseph at DECA. Beer at DECA. Okay, otherwise that takes care of 8th hour, huh? Well, 1/3 hour. Bishop McMahon at DECA. Marie at DECA. Tyler. Alex, no Alex. Oh, they got the thing. Who brought that in? The little camera.
I did.
Who did? Okay, who gave that to you, Tony?
Yeah.
Do you live by him or?
Yeah, he stopped by last night.
Oh, really? Wow. Okay, Jacob at DECA. M's at DECA. Sam, of course, is at DECA. And CM. Boom. Okay, gang, is it up and running?
Yep.
You push the record button, huh? Okay, gang. Hey, what I want to do this morning is, again, continue on with circuits and introduce you, gang, the last kind of circuit. So, again, we talked about series circuit. And again, gang, I like up here, gang, this is a nice, gang, analogy. Gang, a gravitational analogy, gang, of a simple circuit. So, gang, down here we have down here we have the guess what? Hey, what's this the electrical symbol for? Let's pop this out to a St. Nicholas. Again, that's the battery. Again, in the old days, they used that Greek letter epsilon to represent the battery instead of V. Again, V for the voltage. There's a voltage. Again, there's a power source there. There's a battery there, a voltage source there. Again, there's something that's creating a potential difference, an electrical potential difference. Again, charge will always flow. From high potential to low potential. Okay, by definition, we just say in physics that the flow of positive charge is current. So current, the electrical current, is the flow of positive charge. So again, which one of these babies is the positive terminal of the battery? Again, the long line or the shorter one? Let's pop this out to Alexa. The longer one. So again, the way I like to think about it is on that longer line, all kinds of positive charges. All crowded up against one another. They're repelling one another. They want to get as far away from one another as possible. And if you give them a path to get to the area of lower potential, where they're less concentrated, they're going to take that. So sure enough, this right here just represents wire. What does that represent? What do you think? Let's pop this one out to Gus. That's your resistance. That's like your light bulb. That's your electrical device. That's it could be something producing heat energy, sound energy, light energy, thermal energy. It goes through that, and that's when the electrical charge loses energy. Loses electrical potential energy. So we say we have a little voltage drop across here. It runs all the way back to the negative terminal of the battery. So again, I kind of like this analogy here, showing you a kind of a gravitational analogy. Here's the negative terminal of the battery. And the battery, kind of crudely, you can think of it as taking and re-energizing the charge, that coulomb of charge, lifting it up to the higher electrical elevation. So just like water, always be flowing downhill from areas of high gravitational potential to areas of low gravitational potential. That's spontaneous. That automatically happens. It's the same thing with electric charge. So the charge that's on the positive terminal of the battery, is at the high electrical elevation. All the charge that's on the positive terminal of the battery, all on that wire there is at the same electrical elevation. Why again it hasn't lost any energy yet? Again, why it hasn't done any work yet? Again, once it pops through the resistor, then it's done work. And then it loses energy, again, numerically equivalent to the amount of light energy that was produced, the amount of thermal energy that was produced, and the amount of sound energy that was produced. So again, I like that little analogy for a circuit. Okay, we kind of left off here last time, on this one. Boom. Okay, on this slide. Again, all of these ideas now, again, culminating with this slide. Again, this is what they're interested in, again, how much current is going through a resistor. So again, you have to be able to calculate all these things, again, the voltage drop across the resistor, the current going through the resistor, and the wattage of a resistor. Again, that's it. Again, that's all they're going to kind of be interested in, is that you know, again, which one of these resistors has the greatest wattage. Again, which one has the greatest amount of current flowing through it. Again, which one has the greatest voltage drop across it. So again, what we did yesterday, again, we took this circuit and reduced it to an equivalent circuit. In other words, again, all of these resistors that are connected how to one another. Let's pop this one out to Jazzy. They're all in series with one another. So again, that means that they're just connected. There's only one path for the a charge to take. So again, the current only one path. Then the devices are connected in series. So again, we're interested in finding out the net resistance, again, the total resistance. Again, all three of those resistors really act like one resistor that has a value of such and such. And again, whenever resistors are connected in series, hey, how do we find out the net resistance? Again, the total resistance, the equivalent resistance. What do you be thinking? Let's pop this out to Alec. Just add them together, huh? Easy schmeezy. So again, these were all 2 ohm resistors, so 2 plus 2 plus 2 is 6. Again, all three of those really act like one resistor that has a value of 6 ohms. So again, we say that this circuit is equivalent to this circuit. They all offer 6 ohms of resistance. So again, once we find that out, just like when we do Newton's second law, again, if you ever want to find the acceleration of anything, again, you have to know the net force acting on that thing. Again, you got to add together all the forces acting on a system, and then once you know the net force, the total force, the equivalent force, the resultant force, again, divide that by the mass, the inertia, the laziness of the system, that'll give you the acceleration. Kind of a similar thing here. What we want to do is find out the net resistance. And once you know the net resistance, the total resistance, then you can find out the current flowing in the circuit. Okay, and again, we left off with this idea. We found out 2 amps flowing in the circuit. And of course, the 6 ohm resistor is really these 3 connected in series. Again, here's what's important about a series circuit. Again, as we work our way backwards, now this was a very simple one, but we know 2 amps going through this resistor, and we know there's 12 volts across it. Again, which one of those pieces of information, the 12 volts or the 2 amps, again, applies to all of the resistors that are in series with one another. In other words, again, since this resistor is really these 3 connected in series, again, which piece of information carries over? Again, do they all have 12 volts across them, or do they all have 2 amps going through them? Here, what do you think of the let's pops out to Z squared?
12 volts.
So each one of these will have 12 volts across it?
No. The amps.
Yeah, again, it's the amps. So again, whenever you have a resistor that was really a bunch of resistors in series, again, and you know the current going through that equivalent resistance, that total resistance, that net resistance. Again, then you know the current going through all the resistors that made it up that are connected in series with one another. Again, that has to be true because of what important law in physics. So again, we know 2 amps are going through this net resistance. That net resistance was really these 3 connected in series. So whenever you know the current going through a resistor that was a net resistance, a total resistance, of a bunch of resistors in series, you know the current going through all those resistors. That were not true. That would be a major violation of guess what little rule, law in physics. Hey, what do you be thinking, Catherine? Do you remember?
The conservation of energy.
Oh, the other one.
Conservation of voltage.
Of what? Begins with a CH.
Charge.
Baseball practice today, Sturdy?
No.
Oh yeah, because I noticed he's a little more subdued today. Not all fired up, huh? Because that's what starting was yesterday, all charged up, huh? Again, conservation of charge. Another thing, I like to think of it like this, again, what does 2 amps literally mean? Again, doesn't 2 amps literally mean that for every second that you step forward in time, for every second that you pass in, 2 coulombs of charge are flowing past that point? Again, 2 coulombs per second, that is an amp. Again, it's the rate at which the charge is flowing. 3 amps is 3 coulombs of charge flowing past a certain point every single second. Again, 4 amps is 4 coulombs of charge flowing past a given point any single second. 10 amps would be, again, how many coulombs of charge flowing past a given point any single second? Let's pop out to Alexa. 10 coulombs. So again, what we're saying is this. Again, if you take a look at this resistor right here, again, if 2 coulombs come into it every single second, and coming out is only 1 coulomb of charge every second. Okay, where'd the other coulomb go? Okay, charge is being destroyed. No can be. Again, that would violate the law of conservation of charge. Then again, 2 coulombs comes down here every single second. And again, popping off this resistor was 3 coulombs every single second. Oh, where'd that coulomb come from? Again, we made charge, we created charge. No can be. So again, whenever they're lined up one after the other, only one path to take, again, the current flowing through that entire path, that single individual path, again, it has to be same. So again, this is kind of big, this is huge when we get into other circuits, knowing this, whenever you have a resistor that was really a bunch of resistors in series, and you find out the current going through that net resistance, that is the current going through all those resistors connected in series. Again, that's huge, you have to know that. We're going to get into some complicated circuits, and as we start to move backwards, that's what you're going to have to recognize. What this resistor was really these 2, or these 5, or these 6 all connected in series. So if I know the current passing through that net resistance, which was really a resistor that was a bunch of resistors in series with one another, I then know the current going through all those resistors. Okay, so again, that's what we did yesterday. We then applied Ohm's law. Again, Ohm's law is just huge. We keep using it and reusing it over and over again, again, as we break the circuit down. So again, we used Ohm's law to find out, again, the voltage drop across these resistors. Again, if it has 2 amps going through it, and the resistance is 2 ohms, well, 2 times 2 is 4. Ohm's law, the voltage drop across any electrical device, any light bulb, any resistance, will be equal to the current flowing through it times its resistance. So 2 times 2 is 4, 4 volts we're dropping here. And again, when I take the 4 volts that we dropped across here, plus the 4 here, plus the 4 here, hey, how does it compare to the 12 volts here at the source of the potential difference? What do you be thinking? Let's pop this up to guys. Okay, same. Okay, it has to be. Okay, if that wasn't true, that would be a major violation of what law in physics? What are you be thinking? Let's pop this out to, maybe Zach be doing.
What was the question?
If that wasn't true, if 4 plus 4 plus 4, if we didn't get 12, the voltage here at the source, the battery, the power source, again, whatever it is that's creating that electrical potential difference, if that wasn't true, that would be a major violation of guess what law in physics?
Conservation of charge.
The conservation of charge. The other one.
The other one?
Tell him, Catherine.
Conservation of energy.
Conservation of energy. Okay, how do I know that, game? That's not something I really memorized. Game, I think of units. Game, what does 4 volts literally mean? Game, 4 volts literally means 4 joules per coulomb. Game, what it means is this, game, every coulomb of charge that pops into this resistor, when it pops out the other side, game, it has 4 joules less electrical potential energy. So every coulomb of charge entering that resistor comes out the other side with 4 joules of electrical potential energy less than what it had before. And where did that 4 joules of electrical potential energy go? What do you be thinking? Let's pop this one out too. So again, here it is. Let's we'll just make believe that this is here it is, the positive terminal of the battery. So the charge comes up here. Again, has it lost any energy yet? Has its electrical potential changed? What say you, Stern? No, it hasn't. Why hasn't done any work yet? As a matter of fact, gang, we're going to use voltmeters and ammeters to measure current and voltage in a little lab we're going to do. Okay, if I take my voltmeter to measure the difference in the voltage between this point and this point, and you just take 2 prongs, you touch, okay, I'm going to get 0 volts. Why, gang, the electrical potential, the electrical elevation here is the same as here? Why, gang, the charge hasn't done any work yet? Then it'll flow up here, gang, it'll come up here. Gang, has the charge lost any energy yet? What's the heat doing? No, gang, it's still at the same electrical elevation, same electrical potential. Then it comes down here, flows through this wire, Gang, how's the electrical elevation change? The electrical potential change. Has it increased or decreased? Let's pop this out to a negative.
Still the same.
No change, huh? Still same. Then it comes through here, then it comes up to my resistor, which is my light bulb. Now is there a difference in electrical potential? Now it's about to enter the resistor, the light bulb. Let's say let's pop this up to M.
Like right before?
Yeah, right before. No, still no change, still at the same. Then it goes through the light bulb, comes out the other side. Now, is there a difference in electrical elevation between this point and this point? Okay, is there a difference in electrical potential between this point and this point? Let's say let's pop this up to Mason.
Yeah.
Yes! Gang, and that difference is numerically equivalent to the joules of light energy that coulomb of charge created. Gang, this is so many joules of light energy here. Again, what we're saying there is that it pops through that resistor, every coulomb loses 4 joules of electrical potential energy. And then, gang, that charge will move from here to here, and from here to here, and from here to here. And by the way, what's the difference in electrical elevation between this point and this point? Let's say use sturdy. There is none. Gang, why it hasn't, moving from here to here, it hasn't gone through another resistor to do work. So gang, all of this is at the same electrical elevation, the same electrical potential. Only right, gang, if I take my voltmeter and touch here, I get a certain voltage. It's the same as this if I touch here, and here, and here, and here, and here. And if there were a wire there that I could touch, boom, there. So gang, the voltage, we call that a voltage drop. Gang, every coulomb of charge is losing 4 joules of electrical potential energy. Gang, when it goes through the second resistor, it lost another 4 joules of electrical potential energy. When it goes through the third resistor, it lost another 4 joules of electrical potential energy. Gang, that's all it had to lose. Gang, this says every coulomb that exits the positive terminal of the battery has 12 joules of electrical potential energy, more than the charge that's on the negative terminal of the battery. Gang, that's all we have to spend. That's like all the money we have. Gang, if I get a 4 here, and 4 here, and 5 here, that's 13. Okay, that coulomb of charge then lost 13 joules of energy. Gang, where did it get the other joule of energy? We only had 12. Gang, or if it, gang, anything, because this is kind of the equivalent of friction. Really, there is some resistance in the wire. So really, gang, in reality, maybe the voltage drops across the circuit might be a little less than 12 joules per coulomb, because we're really losing a little energy. Again, the wire's warming up a little bit. There's a little bit of resistance in the battery. The battery might be warming up a little bit. In other words, take the joules of thermal energy that's being made and add it to the voltage drop. But gang, we're going to ignore the resistance in the wires. So gang, that's a huge rule, gang. The sum of voltage drops around this loop must be equal to this voltage here. Why conservation of energy? Nate's question?
But did it ever like not use all of its voltage, like have like 12 to start and then have like 2 at the end? So like use 10 throughout the circuit?
Then that can never happen. The only way that could happen is if there was a tremendous amount of resistance in the wires. And it was making, you touch the wire, well, you can tell that's warm, that's hot. Okay, really, in these wires, there's almost no resistance. As a matter of fact, if I take a voltmeter, I think the difference would be negligible. I don't think I could even measure it. Again, you're going to do a lab doing this, and I don't think you're going to really be able to even measure that small difference. Especially here, again, these wires are so thick and big, you really won't understand. Okay, so again, what I showed you here then is this. Just looking at this resistor here, this was the last thing we learned yesterday. We have 4 volts across it. Again, 2 amps is the current through it. Again, 4 volts literally means 4 joules per coulomb, which means, again, every coulomb of charge that passes through that resistor loses 4 joules of electrical potential energy. Again, we have 2 coulombs passing through it every single second. Again, I don't memorize this. Again, I like to think, again, this is the only place in electricity where I want you to show kind of unit cancellation. Again, I want you to show how you got these units over here by doing this. Again, this makes, from a dimensional analysis point of view, again, from a unit point of view, this makes perfect sense to me. Again, this is the rate at which that resistor is doing work. Again, for every second that goes by, for every second that you step forward times, it's doing 8 joules of work, and in this case, again, making the light energy. Or making thermal energy, or whatever the resistor happens to be doing for you. So again, I like to think in terms of, again, knowing exactly what a volt is. Again, it's a joule per coulomb. Which literally means, again, that every coulomb of charge that passes through the resistor, that pops out the other end, it pops out with 4 joules less the electrical potential energy. And when you know the current, again, you know the rate at which that charge is passing through the resistor. Hey, 2 amps literally means 2 coulombs of charge pass through it every single second. So again, if 2 coulombs passing through it every single second, and every coulomb is losing 4 joules of electrical potential energy, again, we lost a total of 8 joules in that second. Again, that 8 joules is 8 watts. So again, in reality, and really this is where I think Physics 1 is going now. Again, they may not actually have you calculate again, the current going through the resistor, or the wattage of the resistor. I mean, I think they're going to do that at some point. But again, it's going to be a lot of conceptual questions. They're going to ask you, okay, which, they'll label these maybe A, B, C, or 1, 2, 3. Which resistor has the greatest current going through it? And why? They may say then, if they think it's all this, if an answer is all the same, well, I'll put all the same. And you're saying, well, that's all the same current. Why? Because they're all in series. And if the current wasn't the same, it'd be a massive violation of the conservation of charge. You can't have 2 coulombs of charge passing 1 point in a series in one path in 1 second, and have 3 coulombs coming out another portion of that circuit. It's just like in a pipe, in a water pipe, again, conservation of water molecules. Again, the rate at which water molecules flow past a given point in a pipe, well, again, is going to be the same. Again, it was less at 1 point in the pipe. Again, well, where's the water going? If it's more, well, where do those water molecules come from? No can be. Conservation of water molecules. Okay, now that, again, I have this down. Here's the wattage of the resistor. Again, I don't memorize this one. Again, this one right here just makes sense to me from a unit point of view. So again, the voltage across any electrical device, any resistor, multiply that by the current passing through the resistor, again, that gives you the wattage of the resistor. But check this out, again. Here's Ohm's law. I rearranged it for current here and for voltage here. Again, if I take, again, this I is the current going through the resistor, well, this I is the current going through the resistor. Okay, in other words, I can put in the voltage drop across the resistor times the resistance of the resistor in for the current, because that's I and that's I, and then I would get this version of the wattage. In other words, again, if you don't know the current going through the resistor, but you know the voltage drop across the resistor, okay, square that, divide that by the resistance of the resistor, okay, that can give you the wattage also. Okay, or, again, I can rearrange Ohm's law like this, V equals I and R. Okay, this voltage, this is the voltage drop across the resistor. Okay, that's the voltage drop across the resistor. So again, that V is this V is that V. Okay, I can put in this IR for that V. When I do that, gang, I get the wattage of the resistor as power, the rate at which it's doing work. Again, I squared R. So again, if you know the current going through a resistor, and the resistance of that resistor, again, you take the current, square it, multiply by the resistance, that'll give you that resistor's wattage. So again, here's the 3 ways that you can express the wattage of a resistor, that you can calculate it, find it out. Again, this is the way I know. And then if I want, I can get the others. As a matter of fact, I almost never even mess with these. I always use this one. Okay, if I know, if I don't know the voltage across the resistor, well, I'll do this to find it out, and then I'll go V times I. If I don't know the current going through a resistor, well, I'll do this to find it out, then I'll use the V times the I. So again, this one, just from my unit point of view, really is logical to me. It makes sense to me. And the less stuff you have to memorize, the better. Okay, gang. Now, gang, again, here's another series circuit. 12 volts still at my power source. That's my battery, the thing that's generating the potential difference. Again, now 2 ohms, 4 ohms, 6 ohms. Okay, not all the same. But nevertheless, gang, all these resistors really act like one resistor that has a value of, guess what? What's the net resistance of that circuit, the total resistance of that circuit? What do you think? Let's pop this one out to Mason.
12 ohms.
Hey, we had 12 ohms. How did he get 12 ohms? Let's pop this out to Jazzy. Yeah, just add them all together. Why gain they're in series with one another? So whenever you have any number of resistors in series, to find the net resistance, the total resistance, then you merely add them all together. So again, let's try that. Let's see if Mason was right. Well, 2 plus, I'm going to go the other way. 6 plus 4, we see that 10. 6 and 4, 10. Then we add 2 to that to make it 12. Ooh, they all act like one resistor with a value of 12 ohms. Now again, if I use Ohm's law, now that I know the net resistance, again, what's the current going through that 12 ohm resistor? Which was really these three in series with one another. What do you be thinking? Let's pop this one out to Nathan. Muy bien, gang. Uno en. Gang, why? The current going through any electrical device, any electrical resistor. Again, from Ohm's law, it's directly proportional to the voltage. The greater the voltage, the greater the current, and inversely proportional to the resistance. Again, the greater the resistance, the less the current. So again, just like Newton's second law, it's logical to me. When I write it A, the acceleration of anything in the universe, again, directly proportional to the net force engaging it. A, and inversely proportional to the mass. Again, it's the same really with Ohm's law. I like writing it like that. Again, the current going through any resistor, directly proportional to that electrical pressure, which we call voltage, the potential difference. Again, you need that to have a charge flow. Again, no potential difference, charge is not going to be a flow. And inversely proportional to the resistance. Okay, now again, gang, this resistor was really, these three in series. Gang, I know I have 12 volts across this resistor. I know there's 1 amp going through it. Gang, which one, the purple or the pink? Gang, applies to all three over here. What say you, let's pop this one out to Alexa. The purple, the 12 volts. Yeah, again, the pink one. So again, it turns out, you know, again, the current going through a resistor, that was really a bunch of resistors in series. Again, you know the current going through all those resistors. Now, again, here's where I think the AP exam is going to be going. They're going to ask you, gang, maybe not, gang, you could calculate it all out if you wanted to. But gang, maybe they just tell you this one has the least resistance, then the next most, and then the next most. Okay, they can ask you again which one has the greatest wattage. Again, the 2 ohm, the 4 ohm, or the 6 ohm resistor. Again, here's the 3 ways. Sometimes when I ask conceptual questions like that, again, I do like to write down the 3 ways of expressing the wattage of a resistor. Again, one of them is sometimes the best one to look at. Again, whenever resistors are connected in series to one another, again, I like to look at this version of it. Again, why? Because I know the current going through all those resistors the same. So again, the current is a wash. So it looks like, again, the one with the greatest guess what? Is the one with the greatest wattage. If they all have the same current going through them. What say you, Alec? Yeah, the one with the greatest resistance. Okay, if these are light bulbs, again, the one with the greatest resistance, is it going to be the brightest or the dimmest? What do you be thinking, Gus? The brightest. Why? Because it has the greatest wattage, which means it's doing work at a greater rate than any of the other ones. It's doing more joules of work every single second and making light energy than any of the other ones. So again, when it comes to a light bulb, it's doing work making light energy. Again, the brighter the light, the more light it be making in a given second. Again, the greater its wattage. So again, these are all in series with one another. Seeing how they're all in series with one another, they all have the same current going through them, and that would be 1 amp. And sure enough, gang, you could, what would be the voltage drop across the 2 ohm resistor? What say you, Ab?
2, 1.
What's the voltage drop, the difference in electrical elevation across this 2 ohm resistor?
Yeah.
I think you had it right before, did you say it? Oh. The voltage drop across that resistor, do you know? Okay, not really. Can you help her out, say Nicholas? Wait. Can you help her out here? What's the voltage drop across that resistor?
2.
Muy bien! Thank you, Helly. Somebody said right, it's right there. Okay, why? Because this is Ohm's law. Okay, the voltage drop across any resistor is, okay, the current going through the resistor, I, times the resistance of the resistor, R. V was IR. So again, that's one of the ways to write Ohm's law. Okay, what would be the voltage drop across the ohm of that resistor? Gain the difference in electrical elevation across the 4 ohm resistor. What say you, let's pops out to Z squared.
4.
Hey, 4 volts. Gain the 4 ohms times the 1 amp. Yep, that's 4 volts. Again, how about the last resistor? What's the voltage drop across that baby? What say you, Matthew?
6 volts.
Hey, gang, 6 volts, huh? Why, gang, the 1 amp times the 6 ohms, V equals IR. Gang, I get 6 volts. Now, gang, isn't the wattage, gang, I like to use this version, 6 volts, 1 amp, wouldn't that be a 6 watt resistor? It's doing 6 joules of work every single second and making light energy. Gang, how about this one? What would be the wattage of that one? Alexa? 4 watts, muy bien. 4 joules of work it does every single second. Gang, not going to be as bright as this one. Gang, what's the wattage of that bad boy? Let's say let's pop this up to Alec. What'd you say, 2 times 1? 2 watts, gang. It's a 2 watt resistor. Because the voltage drop across it is 2 volts. Gang, it has 1 amp of current going through it. That current there, gang, is 1 amp, 2 volts. So, gang, 2 joules per coulomb times 1 coulomb per second. Gang, that is 2 joules per second, 2 watts. That's a 2 watt resistor. Gang, it's going to be the dimmest of the 3. Not as bright. As the 3. Okay, gang, let's get into the only other kind of circuit that we're going to talk about. Then we're going to combine them together, and this is where it gets a little hairy, but it's really not hairy. And I think you're going to find it easy schmeezy. But gang, parallel circuits. Gang, a parallel circuit is one in which the current has 2 or more pathways through the circuit. In other words, gang, when the current leaves the positive terminal of the battery, ooh, it comes to a point, gang. Or, gang, I can go down that road or that road. Gang, when there's more than one road path it can take. It comes to, we call this, gang, a junction. Gang, it gets to the junction where I can go this way, I can go this way, I can go this way, maybe I can go even another way. Gang, then what we say is, gang, once you come up to a point where you can go, take several different paths. Gang, whatever down that way, we say is in parallel with whatever is down that way, which is in parallel with whatever down that way. Gang, that's a parallel circuit. So for example, gang, I have my charge coming up here, and what I can do is I can, here's kind of my junction, I'm calling that my junction, and boom, here's a second light bulb. And then, if I want to build that circuit right there, I can connect any number of resistors I want up to this, huh? Well, one, come over here. Well, one, make my third light bulb. Oops. So again, there it is, 3 light bulbs in parallel with one another. So the current comes up, hits this junction, it can take one of the 3 roads. Again, then we say they're in parallel with one another. Okay, gang, so here is the formula now, gang, for finding out the net resistance of any number of resistors that are connected in parallel with one another. Again, what it says is this, gang, 1 over the total resistance, gang, 1 over the net resistance, gang, 1 over the equivalent resistance. Again, will be numerically equivalent to 1 over R1 plus 1 over R2 plus 1. Again, for how many number of resistors you have? Now, again, if I look at the positive terminal of the battery, again, take a coulomb of charge that leaves the positive terminal of the battery, again, when it comes up here. Again, has it lost any energy yet? Right there, let's pop this out to Alexa. No. Okay, when it comes and moves over to here, has it lost any energy yet? Let's pop this out to gas. No. How about when it moves here to my junction? Has it lost any energy yet? Let's pop this out to Z squared. No. Again, how about if it moves right to there? Has it lost any energy yet? Let's pop this out to Nate.
No.
How about if it was here at the junction, moved down to there? Has it lost any energy yet? Let's pop this out to Sturdy. No. How about if it's at the junction, it moves down this path, this road, and it comes up to this resistor, hasn't lost any energy yet, let's pop this out to Zan. No, gang, why? Because it's all at the same, it hasn't gone through a resistor yet, it hasn't done any work yet. So gang, I'm outlining that all in red. Gang, a coulomb of charge anywhere in red is at the same electrical elevation. The same electrical height, the same electrical potential. Gang, it hasn't lost any energy yet. And it hasn't dropped any voltage yet. Gang, if I take my voltmeter and I touch anywhere in red, I get 0 volts. There is no difference in electrical elevation. Okay, now, when it pops through this resistor, going out the other end, okay, now it did some work. Okay, it made this light energy here. So okay, all along here, bump, 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 all the way right up to the light bulbs. Okay, all the charges at the same electrical elevation. Okay, once it pops out the other end of the light bulb, okay, then it lost some electrical potential energy. Okay, numerically equivalent to the joules of light energy that are being formed. Now, okay, when it pops out the other end, what's the difference in electrical elevation between that point and that point? Let's say let's pop this out to Gus. That point and that point. What's the difference in the electrical elevation, the electrical potential, between that point and that point? There is none. Why dang it didn't go through another resistor to lose some more energy? How about between that point and that point, St. Nicholas? None. How about between that point and that point, let's go with St. Matthew? Gang, the same. Gang, how about between that point and that point, let's pop this out to Z squared. How about between that point and that point, let's pop this out to Mason?
None.
How about between that point and that point, let's pop this out to Catherine? None. That's why, gang, I'm making it all the same color. It looks like a nice purple color. Because everything in purple is at the same electrical elevation. Why, gang, the charge, the coulomb of charge that's moving anywhere in that area, in that portion of the wire circuit, gang, it hasn't gone through another resistor to lose electrical potential energy. Okay, gang, now let's use this formula, gang, to find out the net resistance. Okay, in other words, all 3 of those resistors, and I'm saying they're all 6 ohmers, really act like one resistor that has a value of, guess what? So 1 over the total resistance, gang, the net resistance, the equivalent resistance, will be equal to 1 over 6 ohms plus 1 over 6 ohms and 1 over 6 ohms. Guess what, gang? When they're all the same resistance, it's kind of nice because we have the common denominator. So, gang, I can just add up the numbers upstairs. 1 over R sub T will be equal to 1 plus 1 plus 1. Gang, that's 3. Gang, 3 over 6 ohms. Now, gang, I don't want to know what 1 over R sub T is. I want to know what R sub T is. So I'm going to blank both sides of the equation. Pretty soon you're going to be wearing these, huh? Some of you. Let's say let's pop this out to St. Nicholas. You've got some fancy shoes on there. I can't believe it. Those look like $1 million. Probably still too early, huh? But, gang, I'm going to blank both sides of the equation. Let's say let's pop this out to Mason. I wish somebody was wearing mine. Flip-flop! Yeah, eventually you guys can be wearing flip-flops, huh? Gang, flip-flop both sides. Now I'm going to take the 1, put it downstairs, take the R sub T, put it upstairs. Gang, that's legal schmeagle. As long as we do the same thing on this side. I'll take the 6 ohms, put it up there, the 3 down there. So gang, the total resistance then is 6 ohms divided by 3, which is 2 ohms. In other words, gang, all those resistors really act like one resistor with a value of 2 ohms. Gang, I can replace all those resistors with a resistor which has a value of 2 ohms. That's the net resistance, the total resistance. Okay, notice this, gang. This will always be true. Whenever resistors are connected in parallel with one another. Now, it turns out they were all the same size, but let's say they weren't. Let's say it was like a 6, a 4, and a 1. Okay, find the resistor that has the smallest value. Okay, the net resistance has to be smaller than that. If it's not, okay, you did something wrong. Okay, by connecting resistors in parallel with one another, okay, you decrease the resistance of the circuit. So again, note, resistors connected in parallel always results in a decreased net resistance in the circuit. Gang, I like to think of that like this. Gang, years ago, gang, going up to Door County, it was just one lane all the way up there. Gang, we're driving to Chicago, crowded. Can you imagine all one lane? Crowded, beep, beep, gang, all of a sudden that one lane opens it up into 4 lanes. Ooh, gang, what happens to the flow of the traffic? When the one lane opens up into 4 lanes. What do you be thinking about pops out to Allen? More resistance or less resistance? What's that? Yeah, less resistance. Getting the same thing here. The more paths, the more highway lanes you can take, getting the less the resistance. When you do that, here's a nice analogy. If there's only one pipe coming out the dam, all the water is going to crawl through this pipe to get out into the river down here. Again, the more pipes you put, the less resistance to the flow of aqua. So again, the more things in parallel, okay. Now again, we want to know what the total current is. Let's see if we can finish up this one. So again, that circuit really is like that circuit. This circuit is equivalent to that circuit. All three of those resistors really act like one resistor with a value of 2 ohms. So now that I know the net resistance, the total resistance, I can find the total current flowing in this circuit. How? Using Ohm's law. Take the voltage drop across that net resistance, divided by how much resistance that net resistance has, that gives me the voltage, the current. So the voltage is 12 volts, we're dropping 12 volts across that baby. It has 2 ohms of resistance, but looks like 12 divided by 2 equal to, guess what? Let's pop this out to Nathan. Boy, again, 6 amps. So for this resistor coming into it then, leaving the positive terminal of the battery is 6 coulombs every single second. Flowing into this resistor, 6 coulombs every single second. And flowing out, 6 coulombs every single second. If that didn't happen, huge violation of conservation of charge. The coulombs of charge that come in every second must be numerically equivalent to the coulombs of charge that pop out every single second. Okay, now this resistor really was these 3 in parallel. Which piece of information, the current or the voltage drop across it, applies to all 3 of those? So whenever you had a resistor, if that was a resistor, that was really a bunch of resistors in series, then you know the current going through all 3. But when it's parallel, is the current, is this 6 amps going to be 6 amps going through all 3? It can't be. When the 6 amps comes into this junction, some goes this way, some goes this way, some goes this way. Isn't it true? That's what I tried to show you at the beginning. All of this is at the same electrical elevation, and all of this is at the same electrical elevation. Whenever you have resistors in parallel with one another, when you know that the voltage drop across the net resistance, which is really a resistor that was a bunch in parallel, you know the voltage drop across all of the resistors that are in parallel. What I could do is I could write down there's 12 volts across this guy, this guy, and this guy. They all have the same electrical elevation across them. So again, 12 volts, 6 ohms. Each resistor then has 2 amps flowing. So let me close with this. Does this make sense? They were all the same resistance. They all have the same voltage drop across them. So the 6 amps that comes into this junction every single second. 2 coulombs go this way every single second. 2 coulombs go this way every single second. 2 coulombs go that way every single second. 2 plus 2 plus 2 is 6. That has to be true, otherwise that would be a massive violation of conservation of charge. Okie dokie, gang, have an enjoyable rest of your day, and we'll see you 3rd or 8th hour. Okay, so I made a new circle. This is the different one. So I just changed it. You hitting that screen?